Hello, Mr. Sorrentino here again with another video for our Math 31 course. And this video deals with section 5.3, logarithmic functions and graphs. We started off this chapter with talking about inverse functions, and we were introduced in the previous lesson to exponential function. And we used f of x equals y, or y equals 3 to the x power, as that function to introduce what exponential functions look like and what they do and why they look the way they do. Um, well, they also have inverses, and these inverses, if you would go through and do the inverses shown right here, switching my x's and y's, I'm actually taking the x and making that, which was once um, the exponent, and now making it the result, and y is now in the exponent place. And now when I try to solve this for y, we don't, I mean, until we actually define a function, we wouldn't be able to solve this for y and get that new function. But if I were to graph this function the way it is, as you can see down here, if I could get this to move, there we go, that, this kind of turns like the exponential function on its side. Now, we remember from exponential functions that, first of all, we're only considering bases that are positive. So I'm not going to have any instances where I go, below 0. Well, because of that, this has a domain restriction that I can only put in values that are above 0, because it's impossible for me to raise any positive number to a power and get 0, let alone get any negatives. And so where we had a horizontal asymptote with the exponential function, we have a vertical asymptote at x equals 0 for this logarithmic function. And so in order to solve that equation we have up here, x equals 3 to the y power, in terms of y, we define a function, we call it the log. And it's usually the log base 3 of x. And that's the inverse of 3 to the x. So, if f of x, going back to our notation, if f of x is 3 to the y power, 3 to the x power, then the inverse function, and it is a one-to-one function. Notice that the above does pass the vertical line test as well. It's going to be the log base 3 of x. So these are inverses, and basically whatever the base is here is going to be the base here for that function, for the logarithmic function. Now, one of the things they're going to ask you to do along the way is be able to translate an exponential statement into a logarithmic statement, because that's generally what we do when we go through the process of solving an equation, or solving an exponential equation. We turn it into a logarithmic equation, and vice versa. If I want to solve a logarithmic equation, I turn it into an equivalent exponential equation, and then I should be able to, deal with doing the exponent in that case, or vice versa. So these basically say the same thing. This one here, the exponential statement says, essentially, if I were to read this out loud, and I'm going to write what it would say, it says, get this a little bit thinner, a to the power b is c. Whereas the logarithmic statement, if I want to translate it more into English, I would say the power of a that gives c is b. Or I can even say the exponent a is raised to get c is b. So those are basically the way you would translate that into English. They're basically saying the same thing. one's just saying it a little bit more differently, where I'm going to kind of say, okay, this is designed, if I do a log of some base to a number, I'm looking for the exponent of this base that's going to give me that number. Whereas here, I'm just taking that number, raising it to the power, and getting that result. And as mentioned before, as I mark up this thing here, since exponential functions and logarithmic functions are inverses, keep some things in mind here. As we said before, for a function that's exponential, our a is greater than 0 always. The domain could be any. I can raise this to any exponent I want. Okay, there's no problem with that. The exponent could be anything. The range, on the other hand, well, since I'm taking a number that's positive and raising to a power, it has to be more than 0, and that's basically what this is saying. It's saying basically, I could say that f of x, essentially f of x, is greater than 0, and it's really thick again. So now here, on the other hand, kind of what we talked before, the range of this function becomes the domain of this function, and the domain of this function becomes the range of this function. So the domain, this number I plug into a logarithmic function, it has to be more than 0. Which means, you're not, if you see a statement that says like the log base whatever of 0, or if I say the log base of some negative number, these are undefined. They don't exist. You can't do them. In some pre-calculus, you could actually learn how to handle this and bring in complex numbers, but we're not getting into that in this course. So, but for our purposes, for our logarithmic purposes, the number has to be positive. We're only looking for real solutions for logarithms here. And so, the first one here, given this information that we've looked at, for the example 1a, you're asked to convert the equation log base 4 of x equals a to an exponential equation, and then you're asked to do basically the opposite, convert the equation 5 to the x power equals b to a logarithmic equation. So answer these two questions, and we'll go through the correct way of doing this. So for part A, remember that I always recommend start with the base. The base in this one is 4. So I'm starting with that base, which means that the base of the logarithm should be the base of the exponential function. As far as the rest goes, it's just basically switching places across the equal sign. The x was on the left, so now it's going to be on the right. The a was on the left, on the right, so now it should be to the left. And for me to apply an exponential base to something, that means that a has to be the exponent. And so this is 4 to the a power equals x. In a very similar case with b, this is the base, so I'm going to be starting with log base 5. I'll put my equal sign down, and then I basically am going to have this transition across the equal sign. So the x is going to be on this side, and I always take the log base 5 of a number. And I would also say, for the sake of argument, because sometimes you'll start doing expressions and things like that, get in the habit of thinking of this as having a parenthesis around it. That's certainly the way it's going to be presented on your calculator at some point, because logarithm as well as exponential functions, they imply, they're their own functions. So when you're asked to do transformations regarding them, you have to kind of know where the parentheses are and handle them appropriately. And not any extra parentheses that might be there for extra grouping. There's a couple questions in the homework that kind of deal with that, and they put some extra parentheses in some places, and that sometimes confuses students as far as what's a horizontal transformation and what's a vertical one, because it's based off of whether or not you're inside of a parenthesis. But that's the parenthesis caused by the function, not anything else. So now moving on. On your calculators, if you have a TI calculator, these two are buttons that are actually on your calculator, and these are the logarithm buttons that all scientific calculators will probably have on them. As I said, any graphing calculator is going to have them on there. Um, and this is basically a log base 10. So if you just see log and you don't see any exponential base, you assume it's base 10, and it's same as log base 10 of x. We just don't tend to write it this way very frequently because of the fact that the base 10 is implied if I don't have anything there. Whereas ln, because we had the e to the x power equals y. So its inverse obviously is going to be the natural log, of y equals x. So, so basically the same thing with this, if I'm converting it to statements. So, and ln, it's for natural log, but the mathematician who, was basically accredited for discovering what e is, which is basically, we talked about it before, but it's an exponential base that represents, basically, uh, you know, usual growth or decay of biological systems. He was French, and so he came up with a logarithm for it. It was logarithm naturel or something to that effect. Um, so be aware. I mean, but these are the ones that show up on the calculator. Now, newer versions of the calculator, of the TI calculators. So newer versions of TI-84s. There is a log base command, and what that will do on your calculator is you'll actually see it set up with, it actually will put the boxes here, so you could say you could put, the base here and the number here, and it'll do any log base. But as I said, that's on newer versions of TI-84s. So you have to make sure I mean, it has a certain operation system on them that will have this command on there, and they don't make it easy to find either. You have to either go through the menus on there and search, or you can actually hit alpha in the window button to find that. Um, I'm not going into the ins and outs of using that calculator. You're welcome to use it to your heart's content. However, a lot of the questions you're going to be asked dealing with logarithms, especially once we get towards the final exam, are going to give you things that you have to use various rules and properties that we'll be talking about as we move further into this. But for the time being, you're asked to do the following. For example 2, you're asked to graph um, a logarithmic function. In this case, let me zoom out a little bit here. The log base 4 of x, and use that to draw a graph of this function, which obviously, if log base 4 of x is the main function, this would be a transformation of that function. So let's get into this so we could do this, and I'll just zoom out just a little bit more to fit this in. So now remember, what I'm looking for here for the y's should be exponents that I'm raising 4 to get x. So basically y is going to be the exponent. So what I want here to make log base 4 of x work, I want to have powers of 4. And I want to make sure I have a little bit of everything. So as I come up with those powers of 4, obviously, 1 is a power of 4. It's 4 to the 0 power. So this would be a 0. So other powers of 4 would be 4, 16, 64. Next one would be 256. These represent basically your 1, 2, 3, 4. These are the exponents that would raise 4 to get the numbers that I have for x. And of course, I also want to consider things like, 1/4, which would give me the -1, 1/16, which would give me the -2. And so I'm going to graph this on here, and I'm going to graph it kind of on the light side. I'm going to use a highlighter for it. so 4, 1, 16, 2, 64, 3. The 256 doesn't even fit on here, so basically, yeah, right here. So the graph would do something along the lines of this. And of course that y-axis is the vertical asymptote. So that's a log base 4 of x I graphed there. And I'm graphing it lightly because ultimately I wanted to have the transformation. So now the transformation, I'm just using the same old techniques. I do have a horizontal transformation. I have the -5 inside those parentheses. And the parentheses is being defined by the logarithm. Okay, so be careful. Sometimes they have a tendency to say, okay, well, if I do 2 log base 4 of x minus 1. I'll see they'll do something along the lines of that and say f of x equals that, and then I'll have people say, well, the 2 and the -1 are both horizontal transformations because they're inside parentheses. But remember, the main function is this. In actuality, you really don't even need the parentheses in this version of it. And sometimes they'll even put a number out here and say, okay, it's still the same thing. Those are still vertical transformations. I would just have to distribute this to get rid of the parentheses. The only little parenthesis I'm concerned about here is this one. That's technically around the x, and sometimes they won't even put that around the x. They'll have those gone, and trying to trip you up and making you think a vertical transformation is a horizontal transformation, and sometimes vice versa. But getting back to the question at hand, so here that -5 in there tells me I'm going to add 5 to each of those x coordinates I have over here. So 5 and 1/16 is 5.0625. That would be 5.25. That would be 6, 9, 21, 69, and 261. And as far as the y's go, the 2 is on the outside of that parenthesis, so all of them get multiplied by 2. I did exactly what it says. So this would be -4, -2, 0, 2, 4, 6, and 8. And so when I plot those points, let's see, 6, 0 would be about here, 9, 2 would be about here, 21, 4 would be about here, 69 doesn't really fit on this. Yeah, so that's about the best points I'm going to get on this. So my graph would look something along the lines, recognizing that x equals 5 is now going to be my vertical asymptote, so I want to make sure that 5 would be about here, and they would be my graph. And so those graph transformation techniques still come in handy for us, to graph an accurate version of the function. I just have to know how the original function works, and then if any additional operations I have to account for as I go through and work on that. On to example 3. Example 3. In example 3, this is just about mostly putting this into your calculator, because these things, even if you rewrite these as exponentials, right here, if I consider this to be like, okay, equals x equals x equals x, this is basically this is a log base 10, so I'm looking for 10 to what power is 314. Well, you're not going to know that off the top of your head, because 314 is not an integer power of 10. Your integer powers of 10 would be 10, 100, 1000. So I can say, I can tell you that x is between 2 and 3, but I want to get a better value of that, so that's time to put it into your calculator. Same thing with this. This is basically saying e to what power is 6. Well, e is an irrational number to begin with. It's 2 point, so forth, so forth. What can I do, to get that to be 6? Well, you're not going to come up with a number like that, so it's time to put it in your calculator and just type this in. Here I'm basically saying -5, or take that back. 10 to what power equals -5? Well, that should give you a self explanation at this point, but as far as what that answer is. So take a moment, answer these questions that I'm going to pose to you, and then we'll go through these. So if you do these on your calculator, if you do log of 314 on your calculator, rounding to 4 decimal places, you get about 2.4969. And I do often recommend rounding to 4 decimal places. If you're trying to come up with an approximate answer, for the sake of going back and checking it. If you just like keep 1 or 2 decimal places, and you try to check it like putting it into your calculator and like going back to the original equation eventually or anything like that, you find out like if I try to do 10 to like the 2.5 power, it's pretty far away from 314. Matter of fact, it's 316.22, which makes you think that's a bit off. The more decimal places you keep, though, the closer it is to that 314. So it's better to keep it that way. The natural log of 6 is approximately equal to 1.7918. Again, that's just mostly put in your calculator. For C, it's good to keep an idea about this and always think about it, but also think, you could probably say, well, just knowing what the domain of a logarithm function is, or when it's translated to an exponential function, it should be clear to see that there's no way I could take 10 and raise it to a power that gives me a -5. So essentially here, this is, no solution, or undefined, whichever way you want to say it. It means the same thing. Well, technically it should say no real solution. You can do logarithms of negatives. There are ways of dealing with that. That gets into complex number theory, which is something that is done quite a bit in the pre-calculus course, Math 200. So now for example 4, it's a very similar question, except the fact that these are instances where you're being asked essentially to do things where you should be able to figure this out. Like for instance, log base 3 to 27. I can rewrite this as an equation and say, okay, if I rewrote this as an exponential equation, 3 to the x power equals 27. So I'm looking for what power of 3 is 27. Now 27 happens to be a perfect power of 3. It's, matter of fact, 3 to the x power equals, it's 3 to the third power. So if I have an equation that looks like this, well, 3 to the x power equals 3 to the third power, that means that x would have to equal 3. So try that for part B. What's the answer to log base 2 of 1/8? Well, for this one, again, if I want to rewrite this, I can say that 2 to the x power is 1/8. Now you might be saying, okay, well, wait, is 1/8 a power of 2? Well, it is. First of all, I could do a couple of things to this. I could say, okay, well, that's 8 to the -1 power, going back to some exponential rules. 2 to the x power. Now, 8 is 2 to the third power, 2 times 2 times 2, which means this is 2 to the -3 power. So again, if I have 2 to the x equaling 2 to the -3, that means x has to be a -3. And essentially, you can start taking shortcuts with this. And essentially, if I have, now this one here, I'm not going to go as far as making this an x. I could keep doing it this way, but if I have a log base 10 of a power of 10. Well, if I rewrite, if it's okay, well, what power of 10 is this? This is 1 over 100, which is the same thing as 10 to the negative 2 power. And I mean, in this instance, we're solving equations. But anytime, and we're going to talk about this more as it's defined as a formal property, in actually the next lesson in 5.4. However, I think right here, if you notice it, anytime you have a logarithm right next to exponential of the same base, as long as there's nothing in between them, so there's nothing in here like a multiplication going on or anything like that, then they just cancel. Negative 2. So if I look at the log for D, log base 10 of 10 cubed, well, what is that? Right. These cancel. This is just 3. So for E, what's the answer for the natural log of E to the 5th? Well, as we said before, this is the log base E of E to the 5. And much like I had in C and D, I have a log of the same base right next to an exponential of that same base. Nothing in between them, no multiplications going on onto E or anything like that. That had to be handled something differently. So if that happens, they just cancel, and you're left with just the exponent. Lastly, try D. Okay, for D, takes a little bit of ingenuity here. Again, this is log base E. 1 over E squared is the same thing as me 7 E to the negative 2 power. And that's going back to my exponential rules again. So again, with nothing in between the log base E and the exponential base E, since they are the same bases, just inverse functions, I just left with the exponent negative 2. So those are pretty easy and straightforward. I mean, as soon as you can either do them this way with the equation and kind of figure it out, or use the new shortcut that if I have a log and an exponential that are the same base right next to each other, no other things going on between them, then I can just cancel out those and be left with that. Now, as we get into 5.4, we will have instances where we may have the log base 3 of 4 times 3 to the, X power or something like that, and you're asked to figure out what this is. There are ways of handling that accordingly and coming up with the correct answer for that. So you won't be able to do any cancellation really easily along the way with that, because you have to make sure you handle it correctly. So so this one here, no, you just can't go up and say cancel, cancel. It's going to be 4 to the X power, whatever you want to call it. It's not going to be that. So just keep in mind about that stuff. It has to be a situation where there's nothing in between the log base and the exponential base, and then you're able to do that. Now, when you get to these questions down here, obviously it's a little bit of a problem. 17 is not, let's zoom in a little bit here, 17 is not a perfect power of 4. 3/4 is not a perfect, perfect, like an integer power of 5. There's nothing I can raise 5 to that comes to be 0.75, so, what do I do with these cases? Now, as I mentioned before, if you have that log base formula or command on your calculator, you could use that, and they'll come up with these answers beautifully. The problem is, again, even if you have it on your calculator, finding it could be problematic. As I said, I'm not going to spend time demonstrating how to find it on here, because my goal is not to teach you how to find it on the calculator, just have it do it for you. It's a nice feature, but it's a feature you won't have when you take the final anyway, so you might as well not get used to using it. Even with that, you're not going to be asked to do problems like this on the final, except for maybe setting up the logarithmic statement that will let you come up with the right answer if you put it into your calculator. To answer questions like this, we use what's known as the change of base formula. The change of base formula, very useful, before that command was put into the calculator. Still useful now if you don't feel like searching for it. Um, Basically, it says I could take a logarithm of base b, and we're assuming that base b is going to be a base that, like, that isn't on your calculator immediately. At one time, I mean, even for these calculators, you had a table of logarithms, and they were all base 10. That's how you had to go about doing your logarithms. You didn't have a calculator. You had a table of logarithms. You would look them up. Um, they didn't have one for log base 4, log base 5, log base whatever. They only had log base 10 tables, and so you had to use that to come up with an answer for this. So, and essentially, if I do the log base 10 of m over the log base 10 of b, I will get the same answer. I could also work with natural logs. You're going to notice that I get in the habit of using natural log a lot because I have taught calculus and work with calculus a good bit. And natural log and E are the exponential and logarithmic bases that are most often used in the calculus class like that. And so whenever I go to do the problems now, so if I go to do like the problem for log base 4 of 17, technically I could rewrite that as the natural log of 17 over the natural log of 4. Again, it might be good for you to verify this. Sometimes if you talk and write at the same time, your hand doesn't listen to your brain. Either one of these should work. And if you put this into your calculator to come up with an approximate value, just don't, if you're using log base 10, you make sure both of them are log base 10. If you're using natural log, make sure this is 2.0437 approximately. So again, if you took 4 and raised it to 2.0437 power, you would get, 16.99925. Again, that's a pretty good, that's pretty close to 17. If you're using an approximated value that you come up with doing this, and you plug it back in, and you say, okay, well, the power of 40 gives me 17. Is this the exponent I raised 4 to? If you're keeping the 4 decimal places only, you're going to get a number that's slightly off. Again, the more decimal places you keep, the closer it is going to be the right answer. That's why as we do calculations later, you're going to see that I try to avoid rounding until the very last step. It's basically I do the evaluation at the very last step, so I'm not rounding along the way and keeping exact values. It's your turn though. I want you to try B and find a logarithm base 5 of 3/4 and see where you come up with that. Okay, well, as mentioned before, this is going to be the log base 10 of 3/4, or natural log. I'm just going to do one of them this time, just do log base 10 over the log base 10, which means I don't write it, of 5. And so if I do that, I get approximately negative 0.1787. I would expect, anytime that you have a number in here that's below 1, expect to see a negative when you do that, whatever the logarithm is, okay? Because remember, raising a number to the 0 power is 1. Anything between 1 or 0 and 1, which means you're looking at fractions, decimals, with the number having a 0 in front of the decimal place, you're going to start seeing stuff which comes out to be negative, because that means that chances are, if I'm raising a number to a power, I have to have done some sort of reciprocal, and reciprocals will indicate that you have a negative exponent. Because remember, that's what we're getting here. These are exponents that I'd be raising the base to get that. So basically, if I want to do this, I would check to see, does raising 5 to the negative 0.1787 power equal 3/4. And you would find out it's pretty close. I mean, if I took 5 and raised it to the negative 0.1787 power, if I actually do this, I actually get 0.7500566. Again, the more decimal places I keep, the closer it is to the right answer. Again, as we go through this and do some later calculations, you'll notice that I don't evaluate immediately. I kind of leave the logarithms in place and then evaluate it all in one fell swoop. But that is the end of this lesson and this video. If you have any further questions, please make sure to bring them up in class or come and see me during my office hours. Until I see you in one of those places or until the next video, have a good day and I'll see you around.